Okay, so we're gonna do a workshop today on estimating population proportions. So essentially what we want to do is, we're not gonna know anything about the population proportion parameter P, but we are gonna be given the sample proportion, and we need to use that information with the sample size to be able to determine what should be the population proportion. So we're gonna use a confidence interval for this. So essentially what we want to do is, we need, suppose that we're given n to be 400, and then we're given x to be 100, and we want a confidence level to be at 95%. So we're given n on x, the sample size, and random variables, and confidence level to be 95. Then we want to be able to construct a confidence interval. So to construct a confidence interval, let's see what we need. We have p hat less than the error less than p, which is what we're trying to estimate. P hat plus the error. So then the p hat, what we want to do is, how do we determine p hat? Well, p hat is given to be x divided by n. But since I know what p hat on x and n is, this is 100 divided by 400, p hat is just 0.25. And so now we go back to this and we say, okay, so now we have p hat, so we're good with there. But we still need to find what is e, which is e is the margin of error. So e is defined to be z of alpha divided by 2 times square root p hat q hat divided by square root of n. So now I know what p hat is, but how do I get q hat? But keep in mind, using complementary probability and the second rule probability that says that the sum of all probabilities has to equal to 1 inside sample size. So what we're saying is this: p hat plus q hat is equal to 1. So if I solve for q hat, that just means I'm subtracting p hat on both sides. This goes to 0, and I'm left with 1 minus p hat. So now I know what p hat is. So here I could say, well, q hat now is just 1 minus p hat, but keep in mind, this is 1 minus 0.25, so q hat is 0.75. So now I know what p hat is, now I know what q hat is, now I know what n is because it's already given the problem. Therefore, the next big challenge is to find this guy's z of alpha over 2. So now, what we're going to do is, same thing as we said before, alpha is equals to 1 minus confidence level. So alpha equals to 1 minus 0.95. So alpha is 0.5. But since we need this to be divided by 2, since that's what we're looking for, alpha divided by 2 is 0.025. And this is where we're going to be able to use a z-table to be able to find what is the corresponding z-score when the probability is 0.025. So once again, we're going to use our z-table. For those that don't have one or don't have the book with them, then we're going to be able to use the z-score table from Google. In the previous video, we had said that San Jose State actually has some pretty good z-score tables that we could borrow from them. Just put SJSU z-score table. right? So we're just gonna look something like this. So you should be able to see what we're dealing with. So once again, we're looking for 0.025. And if you notice down here, that we already have the z value of 0.205, which is going to be 1.96. And so we're going to use that, 1.96, to be able to determine what is this missing value, which we do. Therefore, we have everything that we need to be able to calculate what is the actual margin of error for this confidence interval. Now let's actually do that. And once we have that complete, then we should be able to complete our confidence interval. So let's actually use this. Error equals to z of alpha over 2, but we said z of alpha is 1.96 times the square root now of p hat. But p hat we said was 0.25, 0.75 divided by n, but we said that's 400. So essentially what you want to do is you want to take this piece by piece, right? Because I know we're not experts in using the calculator right away. It's going to take some time for us to kind of realize how to use it. So once again, I'm going to resort to my phone. So what I'm going to do is multiply the inside first. So 0.25 times 0.75, we get 0.1875 divided by 400. So 0.8175, we're dividing that by 400. So we get 0.0004685. I know we tend to want to right away eliminate decimal places, but keep in mind you only do that till the very end, because if not, you're actually losing information, which could cause some kind of error. But for the time being, we're just don't have to worry too much about that. But if you do go into higher education, you go to a master's, or even going into research, that's going to be a big problem when you start to just cut off and create truncation error in your numerical calculations. So take the absolute value of that. So the absolute value of this, not the absolute value, the square root of this is 1.96 times 0.02165, 0.6351. And then we multiply that together. So 1.96 times 0.02165063351. So we get 0.04243. So now we're going to be able to round off to the nearest third whole number. So it's 1, 2, 3. So I look at this, and since that's not bigger than 5, then we're going to leave it as 0.42 as our error. So now we go back up here and we construct a confidence interval. Since I already know p hat is 0.25, 0.25 minus 0.42 less than p less than 0.25 plus 0.042. So now we subtract that and let's see what we get. .25 minus 0.042, 0.208 less than p less than 0.025 plus 0.042, so that's 0.292. So this is our actual confidence interval, and we're saying that the population proportion should be within this region. So we could conclude confident that's a true population proportion is within 0.208 to 0.292. And that is the problem. So now we know how to estimate population proportions if we're only given random variables, we're given sample size, and we're given a confidence level. Okay, so this is a couple steps that we have to do, and hope you enjoy the video.